Last session, we talked about ResNets, and we saw that these shortcut connections are going to help us a lot when it comes to training deeper neural networks. Now let's try to expand on that and go a little bit into more details. This is the next paper by the same authors, and they actually want to go even deeper, experiment with very deep networks, like 1,000 layers deep, and see what happens. This is the original network, or the original building block of a residual network. The feature maps from the previous layer goes in. Then you do a convolution, you do a batch norm, then a ReLU, nonlinearity, then you do another convolution, then a batch norm, then you add it to XL using the addition operation, then you do a nonlinearity, and then that's going to be your XL plus 1. What this paper is proposing is that there should be no nonlinearity or no operations on the shortcut branch. All you can do is just an addition. So there shouldn't be any ReLU here. There shouldn't be any batch norm on the main branch, on the shortcut branch. And this is actually the main branch where the information is flowing from one layer to the other one. So I remember one of you asked me, what is the proper way of applying batch norm and nonlinearity on top of a convolution? It was one of the first sessions that one of you asked me about it, and I promised that we are going to go and study it more carefully. This is where we are doing that. So the order is batch norm ReLU weight, batch norm ReLU weight, and then you add it to the residual connection. Why is this important? Let's take a look at the training loss and the test error. The original ResNet, if you try to train it, this is going to be the curve that you get during your training as the iterations of your stochastic gradient descent are progressing. This is the curve that you get for training. Actually, this is the curve that you get for testing. And this is what you get for training error, basically your loss function. This simple modification of doing batch norm ReLU and then your convolution is gonna drop the error rate, the test error rate significantly. At the same time, your network is training better. Now let's see why that's the case. This is a typical form. This is actually the general form that is gonna cover both A and B cases. You have YL, then you do some function of XL, and then you add it back to a neural network. It's actually a neural network block. And then you take the output, which is YL, you push it through a nonlinearity, and you get XL plus 1, which is going to be ready for the next layer. Now let's see some particular form of H and F. If H is the identity and F is ReLU, you get the original configuration of ResNet back. So that's your residual block. And to see it, if H is identity, that's just XL plus the residual. And then F is going to be the ReLU here. And that's the addition. So that's the original configuration. Now let's assume that both F and H are identity and see what happens. We know that it's not identity. We know that there is some nonlinearity there. But let's assume both of them are identity because we want to go towards this formula, this formulation, the proposed one. If they are both identity, you get XL plus 1 is equal to HL plus Caliographic F. Now you can do the iteration and go deeper and see what happens, I don't know, 5 layers deeper, or what happens at the final layer. XL is going to be equal to XL plus a summation of these Caliographic Fs. Of course, with different parameters, but that's what you get. So you can call this another F, and you can see that the information is flowing from a very low level in your neural network to very deep inside your neural network. So there is still this identity structure. So there is still this shortcut path from a very, I don't know, let's call this shallow layer of your network to the very deep ones. Same thing happens when you do the gradients. You are doing the gradient of your loss with respect to XL. That's going to be the gradient of loss with respect to X capital L, the derivative of X capital L with respect to XL. And then you're going to use this formula. This term, we can keep it on one side. And then there is a 1 here plus the derivative of this term with respect to XL. Now this guy has the same structure as the forward path now. Remember, you know this from, because now you're back propagating the errors. This term you know. If you multiply it by 1, that's going to be this term plus some nonlinearity. So you still have the structure that the information is flowing from high up in your network, from very deep layers, to the ones that are closer to your image. So is everything clear? Any questions so far? Now let's see what happens if this doesn't happen. What if HXL is just a parameter, lambda L times XL. So some parameter is being multiplied by your XL. This is not even nonlinear. This is just a linear operation. You're just multiplying it by a scalar. Let's see what happens. You're going to do the same exercise as we just did. That's what you get for XL plus 1. If you do your iterations to go deeper, that's what you get. There are some terms that are being multiplied by your XL, and lambdas are going to go here as well. So these terms, we are going to call that f hat. So that's going to give you f hat, which is just a nonlinearity. We don't care that much about it, but what we care is here. And we know that whenever you are multiplying a lot of numbers together, two things can happen. They are either going to explode or they are going to vanish. So it's either going to explode in the forward path or vanish. What happens to the backward path? This is what happens. Rather than having a 1 here, you have a bunch of numbers that are being multiplied together. So these are problematic. If you have a nonlinearity, that term over there, the product of lambdas, is just, you can approximate it by their derivative of the nonlinear function. So you can approximate it by the derivative of this h. That's a first order approximation, but that's going to give you the idea what happens when you have a nonlinear case. And that's the reason why the order matters of your operations. And it really matters that you don't have any operations on the main path where the information is flowing, basically on the shortcut. And that's why you get a better test error and training behavior. Any questions so far? So you mentioned in the previous session that what about other frameworks? What about other blocks or other formulation? You said maybe you can put a weight on XL. What happens? What if you put a dropout here to drop the information from flowing from one layer to the other one? And the objective is that you want to make your network deeper, or you want to force it to go through the complicated path. What happens in those cases? This is the original one. This is what you have here. We are just removing batch norms. What if you do this? What if you keep half of the input on your shortcut, basically multiply XL by 0.5, multiply the other branch of your neural network by 0.5, basically keep half of the XL and half of the other information that's coming from the more complicated route, add them up together and apply a nonlinearity and see what happens. That could be one option. This could be another option. You put a 1-by-1 convolution on top of your XL. You push it through sigmoid. Sigmoid is a number between 0 and 1. So that's sort of a probability. It's like this, but now these are being learned, these two parameters. You multiply the sigmoid one by the complicated route, and the shortcut route, you multiply it by 1 minus sigmoid, and then you push it through, you add it, and then you do the nonlinearity. This is called exclusive gating. And there are actually some papers who are doing that. And this paper is studying all of those cases and which one is better. You can forget about multiplying by a sigmoid and just keep 1 minus sigmoid here. And basically it's called shortcut only gating. You can put a 1-by-1 convolution. Maybe you want to change the dimension from XL to the other one. This is actually the second case in ResNet where you had a convolution shortcut. You can actually have a dropout there. This one is gonna sort of have a stochastic nature for your shortcuts. Sometimes the shortcuts are there, sometimes they are not, and you want the network to depend less on the shortcut connections and basically force it to go through the nonlinearities. So the paper studies all of these, and because of the reason that I just explained here, none of them is performing as good as having nothing to interfere with the linear dynamics. So basically the linear part of your neural network has to be clear. You cannot put anything to interfere with that dynamics. And the paper also studies different configurations of weights and batch norms. This is the original one: weight, batch norm, ReLU, weight, batch norm. You can have weight, batch norm, ReLU, weight, added, batch norm, ReLU. You can have weight, batch norm, ReLU, weight, batch norm, ReLU, add it back. Or you can have ReLU, weight, batch norm, ReLU, weight. And this is the proposed one that is actually performing the best. So the order matters. Batch norm, ReLU, weight, batch norm, ReLU, weight. Any questions?
Yes, is there some intuitive reasoning as to why that order matters? Or is it just trial and error?
Most of it is trial and error. And at the same time, you can do these sorts of analysis to give you a justification for why this is happening. For some of them, I have a reason. For instance, as you can see, it's always weight and batch norm. So there is always your batch norm on top of weight. So that's the case all the time. For these two cases, we know it's not going to perform because there is some obstacle on the shortcut path. These ones there seems to be no obstacle on the shortcut path, but then it's just a matter of which operation you're doing first.
And could you maybe reiterate, it's still not fully clear to me from that analysis how you know that the shortcut should be, fully linear.
We know that when you go from layer XL to one layer on top of it, there is a linear structure, okay?
Mm-hmm.
That we know. But now we want to do the same thing. We want the information from near our image to go very deep inside our neural network. And we want that linear connection to still exist. And that's what's happening here. Basically you can go from your image to the last layer directly through a shortcut if you have no nonlinearity on H and F. So this analysis is from one layer to the next one. This analysis is from one layer to 10 layers next, or 100 layers next, or 1,000 layers next. And if there is there is a slight change, even a linear one, it's not going to give you what you want because the information is not flowing directly from one layer to 10 layers deeper down the network because there's some stuff blocking the way. Does it answer your question?
Yeah, that makes a lot of sense. Thanks.
Yeah, these two first ones, the analysis that we applied here is gonna explain why. These ones are just trial and error to see which one does better. Any other questions?